All right. So here we go. Lakshman, right? That's the way you pronounce it?
Yeah, or you can pronounce it Lakshman.
Lakshman? Okay,
Yeah,
cool. I always try to get it right.
yeah.
If I get it wrong, just say, hey, Lakshman. I'm like, okay, got it. But hey, always good to have you here. Glad you could, be a part of this interviewing. And then, yeah, we'll just jump on in and get started.
Okay.
Okay, where are you going to high school? Like, how's that been right now? What's going on?
I go to Amador Valley High School in Pleasanton,
Okay,
and it's not going that great because if you heard about like the 60-person party, where like
that was you
50
all, huh?
people got COVID. Yeah, that was at my high school. So we're not coming back this year, but it's okay.
I'm sorry. It's like laughing with like humor and sadness. You're like, oh boy.
It's just outrageous, but it's okay. Whatever.
I mean, that stuff does have an impact, doesn't it?
Yeah, I think it was on like national news because it was that
So
dumb.
your high school is famous.
Yes, we're famous for having a party without any masks on the campus.
It's gonna be in all the history books. In 2020, at Amador Valley High School, the biggest outbreak. I don't
Yeah,
know if that's true, but and what year are you in high school right now?
I'm a junior right now.
Okay, very cool. Did you think you would be starting this year again online after the spring?
No, I thought COVID wasn't that big until like it truly like skyrocketed, and I was like, oh god. So then, yeah, so now I after like maybe May, I was like, oh, we're not coming back.
It's true. I mean, even the hybrid stuff they've talked about the other schools, it's just not happening.
It's not gonna happen either. It's just not that feasible.
It's true. And when did you start with ASDRP?
This summer, started this summer, I believe. Yeah,
So you did some of the pre-work.
yeah, I did. I started with Mr. Harmon Bra, so I
Yeah.
did more computational
Okay.
things in the summer, but then I transitioned to OChem with Edward.
Nice. So with the computational stuff this summer, what tell us about what you worked on?
Yeah, so this summer we worked on, there's this protein, it's a G protein in cancer cells, mostly like colorectal binary tract cancers, called the KRAS protein, and it's part of the RAS family, and it's important in like amplification of cell signaling. And so we were looking at a mutant called the G12D mutant, which is very present in cancer cells, and we were trying to dock and like model the inhibition effects of a thing called benzimidazole, which is a benzene fused with an imidazole, which is a nitrogen on a 5-membered ring. And yeah, so we're looking at various analogs and checking how they inhibited the G12D protein. It's quite interesting. We are going to do a lot more synthesis in the summer, but we really didn't get to it because there's just a lot of time constraints and stuff like that. But
What tools did you use to analyze it?
so first we used Avogadro, which is just a molecular viewing software where we really built the molecules because they weren't that complex to build. They were just like took like a minute. And then we used this thing called Orca, which does DFT, which is density functional theory, where you model like the presence of electrons and other intermolecular forces and its effect on molecular geometry. And then once you have these optimized molecules from Orca, we would take this to Autodoc Vina, where we would dock the benzimidazole to the protein, the G12D protein, and then finally we would view it in something called Chimera, where you can view for hydrogen bonds, which are quite important in the interactions between residues and inhibitors. And we also use this thing called Discovery Studio Visualizer, where you view other intermolecular forces that aren't hydrogen bonds, such as like pi-pi stacking, pi-alkyl bonds, stuff like that.
It's actually really interesting. I've seen a lot of in the things that I look at related to ASDRP, the docking. Like, what does that mean when you say dock it?
Yeah, so when you look at a protein, it has an active site or multiple active sites.
Okay.
And by many papers, there's this website called the RBSC Protein Database, where they have a collection of a lot of proteins and their active sites, all that. And basically what you do is you have to create a parameter file where you have the active site, and you create a grid box of where you can dock your ligand. And basically, you can create different conformers, which are different configurations of each ligand using software such as OpenBabel or other open source things like Balloon.
Okay.
And once you have these conformers, what you do is you dock these and you can tell which ones have the best binding affinity. Yeah, and the docking uses the grid box to do that.
Okay. So I see that and I'm like, okay, how exactly to interpret that? Obviously, you're using it every day. So were you surprised by the amount of tools that were available to analyze this stuff?
Yeah, I was really surprised. It took me. I spent a lot of time actually looking at how they were created. It's really interesting, like the amount of computational software you need just to do something very simple in science is really impressive.
What code is it written in? Its own unique codes?
Yeah, it's coded. Sometimes it's coded in mostly Python because Python's very very manipulatable.
Okay.
So that's what we use. That's what most of them are coded in. There's some coded in other languages, but I think it's mostly Python.
Is Python blockchain? Is that what's used for blockchain? Do you know?
I am not very.
I'm just curious. I know that people talk about it a lot in the CS world, so I'm like, oh.
Yeah, I'm not that.
That's with you name like 4 or 5 different kind of software that have been developed to do specifically what you're doing, and then each subsequent one was like building on the next to keep analyzing a different point of view.
That's why I like it a lot. There's other ones too, like molecular dynamics is where you model protein ligand interactions over time, which is like really complex. I'm currently learning that, but it's very hard. And there's other things such as like you can use like statistical analysis to analyze like results of molecular dynamics and docking and other things like that.
Oh, that's pretty cool.
Mm-hmm.
That's pretty cool. And then you said you started doing, so with the results from the summer, what did you guys do with those? Were you able to publish it or get it written up? How did that go? How did that transition go?
I changed groups, so I really didn't apply it. I know there is a group that is focused on, sorry, dog's getting 11, but there's a group that's focused on making these benzimidazole. I don't think they're having much luck right now.
Okay.
But hopefully they do. But this, as I moved into OChem, I just changed projects completely. So now I'm working on, which is what I was scheduled to talk about today, is the synthesis of a cyclopeptide called cycrophilin F, which is usually extracted from like sea urchins.
Huh.
And it's very, very low extraction yield. Sorry.
This is our dog break time. That's fun. What's your dog's name, by the way?
That dog is Eddie.
Eddie. Is there more than one?
Yeah, there's 2.
Eddie was, as soon as you started talking about sea urchins, right?
Yeah.
He was like, oh, he barked right at that time. That's awesome.
He left, yeah.
So you were saying about the sea urchins. It's an extract that's from the sea urchin, something like that.
Something like that, and it's very low yield. So you have to go through so much of the initial. Sorry, it's not extracted from sea urchins. I meant fungi, but it's extracted from fungi. But you have a really, really low yield of this extraction to the point where it's honestly not very economically feasible to use this widespread in like therapeutical applications. So what we're trying to do is a total synthesis of cycrophilin, and we're starting with a methyl ester tryptophan, which is like a residue, an amino acid, and we're trying to optimize something called the Eschweiler-Clark reaction, in which basically what you do is you take an amine group and you're inserting a carbon in the middle. So that's what we're doing on the end of the indole, because we're starting with an indole and we're running a reaction. But I think that's too specific, I think.
That's really interesting though. So you're inserting a carbon in. What benefit will that do to create the synthesis of it?
Hopefully if we get higher yield than the people who extract it, and it makes it a lot more economically feasible, and then we can probably be able to synthesize cycrophilin F on like a widespread scale and make it more availably used as a therapeutic. because it shows very significant anti-cancer, anti-diabetes, it's antimicrobial, a lot of things.
That's cool. How big is your research group? How many researchers?
Like my group of working on cyclophilin F, or
yours.
Currently I believe we have 7 members, I believe. Yeah.
Are you all doing different parts?
No. Basically, the steps take like a lot of work. So what we have to do is first we have to saponify it with a strong base, and then you have to add acid after.
Okay.
And so what you're doing with the base is you're adding the Bach, which is a protecting group, and then you're removing it with the acid, and then you have to work it up and other things like that. So it takes a lot of time to do each reaction. So by having multiple people in the group, we can do this a lot quicker because people don't come in every day, obviously, because we have other issues like COVID, homework, things like that.
Homework, yeah, exactly.
Yeah. So by having a lot of members in the group, it's really nice when you can work with other people, you can bounce off your ideas, other things like that, and it helps us troubleshoot a lot.
That's very cool. What would you tell a new researcher who just joined your group? Let's say they start in the spring, a brand new person. What would you tell them?
It's overwhelming at first. I feel like, especially in Mr. News group, it's very confusing when you first join because there's a lot of people who are really, really smart and they do a lot of really good work. And when they speak, you think they're literally speaking a whole different language. Like
I believe
I think once you learn the basics of organic chemistry, it makes so much more sense than what you would do when you first joined the group. Like when I joined the group in August, I was so confused.
Oh yeah. So it's just figuring it out. Where did you find yourself in? So it's been really since the end of August that you joined until now.
Yeah, basically.
So where did you feel like it clicked? How much time? A couple months? Was there a particular moment you're like, oh, I see what we're doing?
So I think the reason that I got it quite quickly is because I came in every day for like a good 2 months. Okay. So I came in a lot. I spent a lot of hours, like 35 plus a week. So because of that, I just kind of threw myself in, and the saying "fake it till you make it," that's what I did. I acted like I understood until I understood.
I think that time is key. I mean, we talk about that. You don't learn unless you put the time and energy and effort.
The hours in. Yeah, 100%.
It's how everyone gets good at what they do, the time.
Yeah, it requires a lot of time. Organic chemistry is confusing, to say the least. That's why a lot of college students hate it. So if you're in high school, you have to put time in to understand it.
That's right. You're like, hey, you don't have to do it in college. You can like teach them. What's your favorite part of ASDRP?
Personally, I like I think I just like being in lab. I like the air in lab. It's very like not the air, like breathing, like the environment.
The atmosphere. Yeah, I get you. Yeah, the environment. Yeah.
Yeah, everyone's very helpful and nice. And it's really nice to work with peers who have like the same goals and aspirations as you. So you can bounce ideas off of them, not only in like actual research, but like in life. And it's really nice to have peers like that.
That's cool. I do see that whenever I go down there. The researchers laughing, hanging out. You're right, because you're with people that are like you. They have similar goals. That's awesome.
Exactly. Yeah. Anything else you want to share? Because we're getting near the end of time, believe it or not. It's gone by fast. Oh, It's already been 15 minutes almost. It's crazy. I like it. Yeah. I think I would like to say that people should enjoy doing what they do if they join ASDRP. Because if you join ASDRP and you're not enjoying what you're working on, then you're not going to put the time and you're not going to have the passion. And then you're doing it solely for college apps, which not only wastes your time when you are in lab, but it also wastes time of others who are trying to help you out. So I think you have to be mentally ready to put work in when you join ASDRP.